Hi, welcome to Ollie's Workshop. Today I'm going to take the three-phase brushless motor out of my lathe and wire it up to a variable frequency drive, or VFD, inverter. The reason for that is because I've been running this lathe on a Chinese three-phase brushless motor controller for many years, and it's worked, but it's not been terribly reliable. I had to do various mods to it to make it work in the first place, and it's needed repeated replacement parts, and it seems to have been gradually getting more and more unreliable. So I've decided to cut my losses and get a decent VFD, and today we're going to see if we can work out how to program that VFD to drive this motor. So first off, we've got to get it out. Right, so I've got the motor out. So first off, what is a brushless DC motor and how is it different from a regular three-phase motor? Well, this is a 1 kilowatt three-phase AC mains motor. This is the 1 kilowatt brushed DC motor that came out of the lathe originally. My lathe is from many years ago, nearly 20 years old, I think, 15 years old, and it came with a brush motor. Most of the models that are around today seem to come with a brushless motor, which probably looks something like this. So the construction of a three-phase brushless DC motor is very similar to that of the induction motor. The main difference is that the rotor has permanent magnets on it rather than windings like a induction motor. So in an induction motor, the field in the stator windings induces a current on the rotor windings, and that's what produces the magnetic field and makes it rotate. Because you've got strong rare earth magnets on the rotor in a brushless DC motor, that means that you can have much stronger magnetic field in a much smaller space, and you're not using energy to generate that magnetic field in the first place. So in terms of efficiency, brushed motors are the least efficient. They're 75% efficient. These things are a bit more, probably 80-85%. And then these brushless DC motors are sort of 90 to 95% efficient. So as well as having a stronger magnetic field, they don't have to dissipate as much heat, so they physically don't need to be very large. Whereas, you know, with the lower efficiency of these motors, they need to be that bit bigger to have enough surface area to lose the heat without overheating, basically. You know, it's a physical limitation on how small you can make these things, which is why they tend to be fairly standard sizes. Right, so this motor is currently wired. These are the Hall sensors which are used in a regular brushless DC motor controller. They won't be used with the VFD because the VFD uses the back EMF off the windings to determine whereabouts the motor is in its rotation and when to move the phases round. I've got this wired as a star, so you've got a black and a white, a yellow and a white, and a red and white for each of the windings, and each of the windings are tied together. So I've wired it up as a star. You can obviously wire it as a delta. That might have advantages. I'm not an expert on motors. That's what I decided to do when I got it a long time ago, and it works, so I'm leaving it like that for the moment. Now, I don't know a huge amount about this motor because I got it off eBay. It was only £100, so it was quite cheap. These things are normally £400 or £500. It's odd in that it's 95 volts, which is an unusual voltage. It's not terribly useful. Most of these things are 24, 48 volts, or they're up at 220 volts, so you can run them straight off the mains. What the VFD is going to have to put the appropriate amount of energy into this motor to make it appear as if 95 volts is across the windings. The way that works is outside of what I'm going to go into in this video, but I'm hoping it can do it, put it that way. So I'm not quite sure what the two speeds relate to, whether that's star and delta. Might be. Basically, the way it's wired at the moment, it does 3000 RPM full chat, so it might be that I could get more speed out of it, but obviously that would be less torque. I prefer the lower speed, higher torque personally, so I'm happy with 3000 RPM. Right, because this is 95 volts and 1 kilowatt, it's going to need 10 amps thereabouts of current. Now, you would have thought that a 1 kilowatt VFD should be sufficient, or a 1.5, but no, I need a 2.2 kilowatt because the current rating of the 2.2 kilowatt inverter is 10.5 amps. So that is the minimum necessary to drive this. So I got myself a 2.2 kilowatt inverter. So I know the voltage, I know the current, I know the speed. There's one value that I don't know about this motor, and that's the back EMF. So what I'm going to do is try and spin this at 1000 RPM and measure the back EMF across one of the windings and see where we are. Right, so in order to measure the back EMF, what I've done is I've taken the heat shrink off the star point and attached a meter lead there, and then I've got the other meter lead connected to one of the phases. Doesn't matter which one, they're all the same. Well, they should be. I've got my cordless drill connected, and I've got an RPM tachometer, so I'll be able to measure the speed. Let's just do that now. So we've got a number. That's about 1500 RPM, which is about half the total, or half the maximum speed of the motor. So whatever I read, we're going to be doubling. So what do we get? So we're getting best part of 18 volts there. However, this meter is a true RMS multimeter, which means that it's measuring the root mean square voltage, not the peak-to-peak voltage. And I believe the back EMF is a peak voltage. So I need to multiply that number by 1.414, in order to get the number we're interested in. So quick bit of calculator. So we want 18 times 1.414, that's 25.5, fine. And then we're going to divide that by 1.5, so 17 volts, hoping, is the back EMF constant. So I just looked at the manual, and actually, don't know whether that's going to show up. For brushless DC motors, it should be set to the back EMF at rated speed. So we got 25.5, so that's 51. So we shall set that value to 51 volts. And right, so let's go over to the inverter now and set it up. So this is the inverter that I've bought. It's an Invertek OptiDrive, and it's a OptiDrive E3, which is 2.2 kilowatts, 200 240 volts in, and 1 phase in, 3 phases out. So it can take up to 19 amps on the input. So I am going to have to potentially hardwire this in rather than just plug it into a regular 13 amp socket, because 19 amps is more than 13. Okay, so referring to the quick start guide, we've got to need to have a potentiometer and at the very least a stop and run switch wired in. So let's just wire those bits in. Now I think these are what are called ascending cage clamp terminals. I had a question on these on my last video where somebody couldn't work out how to tighten the wire down, because I think they were winding it up like that and trying to put the wire underneath and clamp it down by undoing the screw. But that's not how they work. You undo the screw, you put the wire in, and then as you tighten the screw, the cage clamp rises up and clamps the wire with the cage. So need to do the same with the potentiometer. So I need to skip 2, and then that one, that one, and that one. There we go. Right, so I've now got speed and start-stop, and I will wire the motor into the 3 output phases here. We've got U, V and W. we've also got a position for a braking resistor and an earth point. In this particular setup, I'm not going to bother earthing it, but I will earth it once it goes into the machine. So I'm just not going to touch anything while it's running. So I've wired up the 3 phases using a piece of screened 4-core cable. I'm not going to wire up the earth just at the moment, just in this setup, but in the final installation I will. And I've then connected temporarily onto the 3 phases. This is just with blades and spades. So in order to work out what to dial into the VFD, I've been through the parameter list that comes in the user manual and jotted down some numbers, some of which I know, some of which I've guessed, and some of which I've determined through playing about with it. So there's not a lot of point me showing you how to put these values in, because all these things are, I mean, they're sort of kind of the same, but they're all subtly different. But effectively, the best thing to do is just go through the list, write down the numbers that you know. There's a hell of a lot of parameters which pretty much I haven't touched because I don't think I need them, and I don't really understand what they do. So for me, it's really this first page, which are the sort of basic parameters, and well, first 2 pages, and then this advanced parameter up here, which is telling it what sort of mode to operate in. And of course I'm doing something subtly different. I'm doing BLDC motor vector speed control rather than a regular induction motor. So I've set it to 3 on that, and then this auto tune thing, which is probably you know, specific to this range of inverters. That's something you, when you turn it on, it makes the motor do some funny things, and works out some values, so it knows what to do with the motor. Now, the one thing I haven't done yet is you can implement a motor temperature sensor. I need to buy something that will do that correctly before I can implement that. So I will do that, but for the moment I'm going to stick this in the machine and see if it works. I may still have to tweak some of these parameters because you know, there are some guesses in here. Right, so we're over at the lathe and the VFD has been plumbed in, motor's been reattached. Now, because I'm difficult and I've got this control on the saddle, I needed to plumb that in to make this stop and go. Now the forward reverse and the stop start inputs are referenced to the 24 volts output on this. My control board is only 5 volts for the handle over there, and that means that I needed to shift the levels. To do that, I've used some opto isolators, and I've just made myself a little daughter board which sits on there, and then comes back up out to here. Haven't quite worked out where to sight this yet. I think I'll put the lathe back, because at the moment it's out, so I could get to the back to get the motor out. Once I put it back, I'll work out where it's going to go, because obviously it can't stay there like that. Now, moment of truth. Right, so let's turn it on, see what it does. So it says stop at the moment, that's good. Turn the speed down. Ooh. So stopping and reverse. There it goes, forwards. Lovely. Okay, now at some stage I want to wire my foot pedal in to act as an emergency stop. So I've programmed the inverter to do a rapid stop when the power is removed. That's a feature. However, I have just discovered a problem with it. when I turn the lathe on, if I can kill the power at a slowish speed, it stops rapidly. That's fine. Just have to wait for this to run out of power. It seems to stay up for a good 20 seconds under its own stored energy. Right, so try again. If we turn the speed up a bit and hit the stop, we get an error. That according to the book is an output over current error. Not quite sure where we're getting over current, but it's probably a symptom rather than a cause. So I think that means that I need a braking resistor. So I will attempt to find one of those. Now that's all working, basically. I think that'll do it for today. I will do another video where I wire the foot pedal up to the NVR, because I think that can stand on its own, really. It's definitely a worthwhile update to any machine tool, really, to have an emergency stop pedal, so you can just stamp on it should you need to. Kind of fancy putting one in for the drill, and hopefully by then I'll have a resistor to wire into this, and we will hopefully get that emergency stop to work really nicely. Alright, thanks for watching. See you next time.